Thank you very much. I would like to request everyone present in the hall to kindly keep your mobile phones on silent mode. We are also grateful everyone joining us online. Throughout this week, we are hosting a workshop in condensed matter physics with participations mainly from beginning PhD students. The workshop has brought together a series of lectures by distinguished speakers from various reputed institutes. We are especially happy that the workshop participants, PRL members, IAPT members, members from Booty Foundation, and our other invited guests and visitors have all gathered here this evening for the 8th PRL IAPT Dr. Vikram Sarabhai Lecture 2026. To formally welcome and address the audience, it is my pleasure to invite Director PRL Professor Anil Bharadwaj to this event.
शुभ संध्या, सुस्वागतम, अभिनंदन, नमस्कार, केम छो, राम राम, राधे राधे, वणकम, आदाबर्स, सत श्री अकाल, and a very good evening to everyone. Today we have two-in-one session. One is that we are hosting the workshop on condensed matter physics, which started on 9th of March. So today is the middle of that workshop. And we combined this workshop with another event, which is the PRL IAPT Dr. Vikram Sarabhai lecture. Today is the 8th lecture in the series of this lecture, which we started in 2019 on 7th of February, to be more precise. And since then, we have been hosting this lecture series uninterrupted. In spite of COVID, we are doing it online. And then in 2023 onwards, we came back offline mode. In addition to this, we also have colleagues from our Booty Foundation with us. And therefore, I would like to welcome firstly the delegates of the workshop, the speakers of the workshop, the members from IAPT, that is Indian Physics Teachers Association, right? IAPT, oh, Indian Association of Physics Teachers, sorry. Indian Association for Physics Teacher. And then, of course, the Booty Foundation and my own colleagues from PRL who are assembled here for this special event. We are also welcoming all the delegates or the listeners online on the PRL YouTube channel who are watching us live. And those who could not watch us live can watch us live, can watch this event on the PRL's YouTube channel because it gets archived there. My special welcome to veteran Professor K.N. Joshipura with us. He has been there since ages. I don't know how many years old he is now. 75 years old. So please have claps for him. और आपको मैं बताना चाहूँगा इनका पूरा नाम क्या है. इनका पूरा नाम है कमल नयन जोशीपुरा. कमल आप जानते हैं? कमल नयन. ओके, जोश एंड पूरा. सो कमल नयन जोशीपुरा. ओके, अब आप लोगों को याद रहेगा, राइट? So he has been there in many of the events of PRL and he has trained many PhD students, and he has been still very active at the age of 75 as a part of teaching physics, guiding students, and still continues to do that. And he has impressed upon that about 9 years back, actually, that we should start a series of this PRL IAPT. And then I said, okay, we can do that. So it started in 2018, right? The dialogue started around that time. And then we said, okay, we will start this as an annual series of lectures. And it became a very prestigious in terms of its importance because it is delivered by eminent scientists. And today we have yet another very eminent scientist among us, Professor Dibyendu Chakrabarty, who is going to give the 8th PRL IAPT Dr. Vikram Sarabhai lecture. So he is here with us. Please welcome him also formally. Currently, the president of what you call regional chapter, right? Regional council. Professor PC Vinod Kumarji is there with us, who is the president of the Regional Council 07. And he will be actually telling us more about IAPT and what it does and how it is actually helping the students, the teachers in growing the understanding of the physics, which is also very, very important for us as the community grows and make understand what is new, which is happening in the area of physics. So please welcome Professor PC Vinod Kumarji, who is the president. We have two colleagues from Booty Foundation with us today. Mrs. Sorry, I'm not getting the name. Veena, Veena, right. Mrs. Veena, who is niece of very renowned PRL colleague, Professor Bimla Booty, who has been in PRL for almost like 4 decades. And she has formulated a award which is called Booty Foundation Award, which is being arranged by PRL, but provided by the Booty Foundation. And we have Mrs. Veena and sorry, Venkat, right? Sorry about that. So they are there with us today, and they are also being a part of PRL family for a very long time now. And Venkat has actually worked PRL, and they are with us on many occasions. So we welcome both of them. And so with this welcome address, I would like to thank you all for coming. In addition to this, of course, we have students who have come to attend this lecture, the PRL IAPT lecture, for them to understand what is happening in the area of space science, space weather, on which our renowned Professor Dibyendu Chakrabarty is going to tell us what is new happening in this area, and also to the delegates of this workshop. Though you have been taught about condensed matter physics, but now you will see what linkages condensed matter physics has with the space sciences. So this is the task I'm giving to Dibyendu to connect these two to make people understand of physics is everywhere, wherever you want to apply. Thank you and welcome.
Thank you very much, sir, for your warm welcome and for setting the stage for this evening. We now move to the next part of the program. We now invite Professor PC Vinod Kumar, President IAPT RC07, to speak briefly about IAPT and also introduce our distinguished speaker and invite him to deliver the talk.
Thank you very much. Honorable Director, Professor Bharadwaji, Professor Kamalanayan, KNJ, we say KNJ with the short, Professor Dr. Ramani and his family, today's speaker, Dibyendu Chakrabarty, the participants of the condensed matter workshop, which is going on at PRL, other participants, life members of PRL who are here presently, and students and ladies and gentlemen. It's a great occasion and honor for me to introduce about the IAPT activities. So IAPT is almost 42 years. So IAPT almost crossed middle age, we can say 40 plus. So it has now this year, last year also I have mentioned many, so many of you must be common and listening about the various activities of IAPT. Since its travel from the last 42 years, it has grown to acquire at least 10,000 plus life members, spread all over India as well as outside in foreign countries. So though it is initiated by Professor Kandelwal, we still remember him and his colleagues for such an initiatives to encourage physics teachers to inspire the new generation. So teachers are very important. A teacher community and this association is, it's not a political association. It is an association not for demanding some requirements of the teachers. It's an association, it's a voluntary association which will be working for inspiring teachers to inspire the students. So various activities are conducted across all ages of learning or the people, whether they are students in school level, whether the students are at the college level, they are at the research level, they are at teachers at junior colleges, maybe researchers at the institutes, researchers at universities, professors of universities. So it is a huge collection, huge bandwidth of people who are some or the other way linked with the subject physics. So many activities you can find. I am not going to list everything, all activities that we do at IAPT at the national level as well as RC. IAPT has now around 24 regional councils. IAPT major body has been distributed their work through regional councils, and we have around 24 regional councils. Gujarat region comes, Gujarat and then Daman and Diu, and that is the Regional Council 7. So we comes under Regional Council 7, and we have around 400 plus life members within Gujarat. And many life members are students, many life members are research scholars, and many of them have retired from their regular activities as a teacher, professor, scientist. So this is the situation as far as RC07 is concerned. Indian Association of Physics Teachers publishes monthly magazine, which is called the IAPT Bulletin, every month without any break. Now these bulletins are circulated freely to all life members, and it can be seen from their life member Gmail or mail ID. It can directly come. Those who are opting for a hard copy, they are arranging to send the hard copy as well without any payment. Just be a life member, and then life member will be getting a copy of this regular bulletin. This bulletin has got special features because it addresses the issues concerned with the physics teaching. It will also highlight what are the latest research activities or research outcomes that are published elsewhere in various scientific journals, a highlight of that. There can be certain problems which are solved maybe at the national level test conducted by IAPT for the students, and solutions and clues how it can be attempted, what are the ways such a problem can be solved, and a few reports coming from various regional councils, what are the activities and how the participants are enjoying and where it is reaching, to whom each of these activities are reaching. So whether it has reached to the concerned, what our objection is or not. RC07 has published another publication which is called the Pragami Tarang. It has started again around 18th issue. 17th issue is already out, 2025. And the 17th, 18th issue will be prepared starting from the lecture that we are having today. So one of the prime article that will be published in Pragami Tarang will be the article that is related to this Vikram, IAPT, PRL, Sarabhai lectureship that is awarded to Dibyendu Chakrabarty. So I request you that after the lecture, you have a task of preparing a semi-technical, because it is addressing not scientists alone, it will not be addressing only the students alone. So there should be a semi-technical report of around 4 to 5 pages will be published in our Pragami Tarang journal. We have last 2 years onwards, we have started convention, regional level convention. We used to have a state level competition for innovative experiments. This competition was arranged by the regional council. At each cluster level, regional councils are further divided into 10 clusters to occupy even different districts and of Gujarat. So we have around 10 clusters, and each cluster level there will be a competition for innovative experiments. Who are the participants? Students at the school level, students at the college level, students at PG and research level, and as well teachers separately. So all level of stakeholders of physics, all of them are stakeholders except their parents. So they are there are some competition at each cluster level. The winners of those cluster level will be competing at the state level, and the state level winners are being nominated to compete at the national level. So this is where we are. Every year we used to have this state level competition for the innovative experiments. Anyway, we are at the state level. All these competing participants and teachers accompanying those students used to come. So we thought that why can't we convert that into a convention? So we have a regional council convention, and that is along with this innovative state level experiments. So this is the last year, 2025 we had, 2026 we had completed, and 2027 I hope this will continue. This is another new activities of RC07 that we have initiated. Now related to reach out to the teachers as well as students, as far as the magazine is concerned, Pragami Tarang, where beautiful article they appear in that. So beautiful in the terms of subject content. I'm not saying that beauty related to subject content of that. So then we arranged a quiz program at the state level, online quiz program, where this online issue of this current Pragami Tarang will be circulated to all the registered participants. Registration is free of cost. And then there will be an online test conducted, online quiz test conducted based on all the articles appeared in that. And this we have continuously doing it, and around 500 plus students and teachers, as well as whoever, even in their parents wanted to appear, read and appear, they are also allowed. So they are called physics enthusiasts. So they can also appear and register and appear for this quiz program. Generally, what we find is that maybe because it is free, 600 to 700 will register, but at the end, when they appear for this contest, there can be around 200. So a large reduction. So we want to encourage that let this various stakeholders read these articles which are related to latest developments occurring in our in physics. So this is a concern. Along with, there are many other concerns which we would like to address, all of us together, because the number of students now choosing science in general and physics and mathematics in particular is falling in a very great, right, level of decay. School level itself, students are not choosing science. At the HSC level, if you see the number of students who are chosen science subject is very, very low. We have a very good population of youngsters, but when you see now for the future, we will not have sufficient scientists available who have got some basic training in science as well as physics and mathematics in particular. This is an issue being discussed at the national level, at various centers of our cluster as well as regional councils, how to address this. When we discuss openly this with the school student, maybe HSC level students, then the report that we gather suggests that गुजराती में बोले तो अगरू लागे छे physics and mathematics अगरू लागे छे. Now अगरू लागवा माटे there are certain problems and the teachers are essentially important in that component, right? Gujarati is अगरू मुने मजे लागे छे because no, I have not been trained in Gujarati, right? The problem of training. So physics teachers cannot take their hands off of this current situation. So this is a very important aspect that IAPT at the national level as well as at the regional level is facing and addressing at every level. So collecting or all such issues, how different regional level, how the different state level, they are working to encourage and inspire the students to take basic science first at the school level. And then later on, they may land up to take physics or mathematics. So that is a major activity and responsibility lying on all of us. Because major problems of the nation cannot be handled by the seniors. Seniors will come and retire and then they will leave. We need to present our youngsters. Next generation has to be trained. For this training, I think IAPT and RC07 is struggling and working very hard at different levels to first encourage the teachers on addressing their problem. What are their problems? Why they are unable to inspire the students to take science? We find many of the school level or the college level itself, though they are PhDs of physics, they themselves are somehow not inspired. This is a fact. Somehow this is not overcome, then we cannot do anything. So it is not all the time, support and financial support is important. Also from within, one need to understand the importance of the subject. Particularly because now we are entering into a new technological era of what is called quantum technology. For the quantum technology, for example, initial level, at least when it is developed to a technological level where it is being able to use, purpose of using for the public utility point of view, physicists has to be behind in the initial level of development. Without physicists, I don't think any new technology can come up to that level of usage to the society. So this is a common concern for all of us. I request all the scientists who are here, whenever they get a chance, please try to encourage your neighborhood, including parents, including your students. The society as such has to be somehow get inspired by the various activities which are happening, various discoveries that are happening, various new technologies which are being developed. This is a request from IAPT, RC07, and as well as on behalf of IAPT national level to all the participants here. Please try to influence your neighborhood. so that tomorrow we will not be without, devoid of physicists in the society. Many places, the word physics is again treated with an eyebrow raising, right? Physics. So that is the level of maybe the difficulty, or I don't know what that means, but you understand the problems. So I think with this small introduction, I will now give a brief introduction about today's speaker. As Professor Bharadwaj told that this is the eighth continuous effort of PRL as well as IAPT together. This year, it is little early compared to last year, but it happened that it is in the middle of the examination. So many of the participants, wherever we sent, they are saying that, sir, it is difficult for us to come, including our secretary, RC, said that they are busy with the examination schedule. So either it can be later or it can be little earlier, so that many more teachers from universities and other places can be accommodated. Still, I think it is done nicely. We appreciate the efforts of PRL and the speaker getting ready for this particular day. Now, talking about this eighth PRL IAPT speaker, Professor Dibyendu Chakrabarty has been a leading, he is already a head of the Space and Atmospheric Science Division of PRL, and is also the principal investigator, PI of Aditya Solar Wind Particle Experiment, ASPEX, on board to the Aditya L1. We're all familiar with the Aditya L1 payload. For the upcoming Disha, the disturbed and quiet time ionosphere thermosphere system at a high altitude mission. A proposed twin satellite aeronomy mission by ISRO. He is the science PI of the VRAD, the Venus Radiation Monitor instrument on board the Venus Orbiter mission of India. In addition, he is involved in the science and instrument plan for the Mars lander mission, as well as the Chandrayaan-4 mission. I think these are all forthcoming mission of the ISRO mission of India. He is also involved with many other activities of ISRO as well as other space science related agencies. To list few, is the member of the working group of Pillar 2 International Program, which is called Presto 2020. He is an editor choice of Space Weather for 2 papers. He is a member of RAC IASCS Kolkata 2023, life member of Indian Planetary Science Association, life member of Indian Radio Science Society, member Board of Studies Space and Atmospheric Science course, UN CSI CSTEAP Center for Space Science and Technology Education in Asia and Pacific. It is being conducted at PRL, I think, right? We used to have a course here. So he is a chair of IPSTRA panel for solar terrestrial physics, Bangalore, and a list is continuing. I don't want to spend more. He can go on through, one can go through his website and then find around more than 5 to 6 pages of his achievements apart from the publications. I'm saying only what he's involved with. So with this brief introduction of his abilities and involvement in our space program, ISRO program, I invite Professor Dibyendu Chakrabarty. First of all, I congratulate him and giving on behalf of IAPT, thanking him for readily accepting and sparing his time for this particular day. I also welcome you all for this function and on behalf of IAPT and RC07. Thank you very much.
Good evening to all of you, and it's a matter of great privilege and honor to be able to stand here and deliver this lecture. First of all, I express my sincere gratitude to Director PRL for nominating me for this lecture. I am grateful to our IAPT colleagues and Professor Joshipura, Professor Vinod Kumarji, and others, and from the Professor Bimla family representative who are here. I also thank the Theoretical Physics Division who are organizing this great conference. Director PRL was mentioning that condensed matter physics and space physics connection, there is a lot of connection, not in terms of directly in terms of science, but in order to do that science, the kind of detector and other instrumentation that we are doing, without condensed matter physics, it is not possible. Any detector that we are using, I think there is a condensed matter physics in it. And I thank you, the students and all my PRL colleagues who are here to listen to this talk. And with this, probably I will start today's talk. The title of the talk, when I was thinking, I was wondering what kind of title will suit today's context. Yeah. So, am I audible? Yeah. Yeah. So the title of today's lecture is "The Mood of a Star and Space Weather." Now, to start the talk, I was just thinking that what exactly I mean by the mood of a star. Stars are culturally associated with we look at sky and look at the stars, and there are literary articles and other kind of poetries, and everything is associated with stars. And it's not open. Okay, so this is a famous um, painting by a famous painter, is a post-impressionist painter, Vincent van Gogh, who in 1889, this is the titled as The Starry Night. Okay, and you see various features that he has painted on this painting, and among them you see moon here. It's not working. Battery is not. So among them, you see moon here, you see Venus here, that is identified. You see a lot of stars here on the sky. This painting, Van Gogh was actually mentally disturbed. He was put in a mental asylum. He is looking out of the window and looking at the sky. It's early morning hours. Probably that is the reason why there is a hue of light here. And then he is looking at the sky, looking at the stars. It actually captures, so in a sense, the stars reflect, the reflection of stars, the projection of stars into the mind of a person is something very important for creative people. Okay, so stars have played a very important role to trigger imaginations for us. Now, when we flip the question upside down, we are today going to talk about the mood of a star, not the mood of a person on which stars have an effect. Okay. The mood of a star, when I mean, I'm not going to talk about every star. I'm going to talk about a particular star, which is our sun. And in sun this is our galaxy, and it's the galactic center. And if you look at somewhere in an insignificant arm of the galaxy, spiral galaxy, sun is there, and sun is moving with a speed of 26 kilometers per second through something called local interstellar cloud, LIC, not Life Insurance Corporation of India. Okay, local interstellar cloud, and going through that, the sun is going through that. If you actually zoom it in, you will see a certain feature which looks like an eye. This feature is imagined. Okay, the outer feature which looks like a tail is imagined. We don't still have enough idea of how it looks like. This is just an imagination. We really don't know the shape of this particular structure, and I'll point to you that why it is so. The sun is at the center, and you see three important features there. One is termination shock, where solar wind, when it is coming from the sun, it is supersonic. When I say supersonic, it moves greater than the speed of the sound. Sound in that medium, because sound velocity is dependent on that medium itself. So dependent on the sound speed, the solar wind is supersonic. And at this boundary, it becomes subsonic. So this is the termination shock. The region which we call the helio sheath here, and then the solar wind actually slows down here, and eventually outside it is local interstellar medium, which we called as LISM, local interstellar material, and there is a boundary where solar wind ceases to exist beyond that. So this is more or less the position of our star in the entire scheme of things, which is not so significant star. You don't even see in terms of brightness, not so bright, not so big, but it is there somewhere in the corner in an arm, which is not so significant. We are standing there in somewhere inside on a planet. So this is our setup, okay? Now, if you zoom in, this is the sun, and this is the termination shock I was talking. This is helio sheath, and you see heliopause. As I said, we don't know about the shape of the heliopause, and only information we have so far is the Voyager mission in 1970s, which in an angle of 40 degrees went this way, Voyager 1, and Voyager 2 went this way. And now they're in the interstellar medium. So they have gone out of heliopause, and still some of the instruments, they are still working, and we are receiving the data. How long, we don't know, maybe another 1 or 2 years. We may still get data. NASA is actually conserving the energy the way they can. And then what is there in this medium is mostly neutral. Is a two-third of the material is neutral, 1/3 is plasma. And this part is a lot of uncertainties with that, how it looks like, because most of the two satellites which have gone there, which has gone through the nose of the heliosphere, because the sun is moving here, one has gone here, another has gone there. Whether it looks spherical, whether it looks like a tail, we don't know. Only one satellite, which is Pioneer 10, went towards the tail. Okay, and we don't have, because it's enough information from Pioneer 10 to actually infer that what kind of shape we are talking about. Now, you see, I'm not getting into the details of it, but what I'm saying is that as you move outward from the sun and going towards the boundary of the heliosphere, Helios is a Greek god of sun. So its heliosphere means an entire area which is dominated by the sun. And then you see region of heliosheath, and you see heliopause and local interstellar medium. There are characteristic variation in terms of how solar wind behaves. And you see those jumps and decreases accordingly, and you can identify that these are all based on Voyager observation. Okay. Interestingly, when you look at the energetic particle like cosmic rays are coming from outside the galaxy, most of the time coming from supernova explosions or black holes or neutron stars from there. Cosmic rays, very energetic particle. The most energetic particle that you can conceive in the universe is cosmic rays. They're coming, and these are the sunspot variation, means sun is active and passive the way it is going. So this is cycle 21, cycle 22, 23. These are the Voyager observation of these energy ions. What I wanted to point out in this curve, that the cosmic ray fluxes are actually anti-correlated with the sunspot activity. You can see this is maintained, but the moment Voyager goes into heliosphere and outer sphere of the heliosphere, like you go to termination shock or heliopause, you see this anti-correlation breaks down. That means you are getting into a medium which is not controlled by the sun, because cosmic ray variation inside the heliosphere is greatly controlled by solar magnetic field. The very fact that it is not following anti-correlation, that essentially suggests you have now reached a position where solar magnetic field is not the dominant player. Okay, so that's a very good observation and probably once in a history kind of observation. Now, does it mean that we can't get anything from outside the heliosphere? The answer is not entirely correct. We do get particles which are coming from the local interstellar media. Because most of the particles are neutral, they are not obstructed by magnetic field. They come inside heliosphere. Once they come, they get ionized by solar radiation like ultraviolet and extreme ultraviolet. They get ionized, and then solar wind picks them up because solar wind has a magnetic field in it. So it picks them up and it carries them along with it. Those are called pickup ions. And those pickup ions originally are coming from local interstellar medium, but you get it even at the orbit of the Earth. It comes from that far to this position. And so once you study the pickup ions, you have some sources to actually infer the local interstellar medium properties. So that's the way scientists approach it. This is a revolutionary observation in some sense, in my view, because looking at an orbit, sitting at an orbit which is 15,000 by 36,000 kilometer orbit, which is here, this is the magnetosphere, this is Earth, and this is the orbit of the IBEX satellite. And what they are looking at those energetic neutral atoms. See, these pickup ions, when they come, they actually carried by solar wind, they go outside the heliosphere, they become, through charge exchange process, they become energetic neutral atoms. So they exchange charges with interstellar material, and the interstellar neutral atom become energized. Now they don't obey magnetic field, they come to the Earth's orbit. Very less in number, nevertheless, they do come. And what these people planned an experiment from here, that they look at the energetic neutral atom that is coming towards the Earth. From the Earth's orbit, what they saw is something remarkable. What they saw, that there is a band of energetic atom, and if they in the heliopause or heliosphere, they look like a band. It's not a diffuse one, it's a band. And if you superimpose on it by the modeled interstellar magnetic field means which is outside the heliosphere, you will see this maximum intensity of those energetic neutral atoms are coinciding with when it is perpendicular to the magnetic field. Now, there are various theories for it. This issue is not settled, but this is a remarkable observation, and it shows that the energetic neutral atom that is coming and the way the interstellar magnetic field is draping the heliosphere and the way they are distributed outside the heliopause is something which is not uniform. Okay, it greatly is controlled by the magnetic field that drapes the heliosphere. Now, sun itself is a bit peculiar in the sense that you go closer to the core, temperature increases. At the photosphere, the temperature is around 7,000. You go to convective zone, which is above that radiative zone core. Once you go to core, you get a 15 million degree Kelvin temperature. And then you come out, you are coming away from the source. The sun photosphere is 7,000 degree Kelvin. Again at corona, it becomes million degree. So that means it's counterintuitive in some sense, because you are going away from the source and temperature is increasing. This is the famous coronal heating problem. Okay. So scientists had a difficulty in explaining initially, and many theories have come because of that. I'm not getting into the details of it, but certain part of it is understood. But in totality, it is not understood to the extent that the scientists will be happy about. So if you come away from the source, your temperature is increasing. So that is something, the problem that lies with the thing. When I say the mood of a star now, sun itself being a star, its activity is not uniform. It has a cycle which varies, waxes and wanes in 11 years. It is very active on 11 year, in 6.5 years, and then it becomes again low in activity. It's quiet at that point of time, almost meditative. And then it continues. But on top of it, there are large period variations I can see. So this is the modern maxima that is written here, where the solar activity itself has gone up. So this is a different kind of period that we are talking about, not the 11-year period. And then, for reasons which is not known to us very well, there are periods in the history and which associated with ice age over the entire globe. In many places, there are different kind of temperature drop or ice age formation. You see there is Maunder minimum for 70, 80 years. The sunspot went to almost like non-existent. So sun became very quiet at that point of time for reasons we don't understand. There is also a period around 1800, which is called Dalton minimum. There also it happened. Now, so that essentially means that sun itself is changing in activity at different time scales, and sometimes it appears to be aperiodic. And that is where a lot of problems come, because that comes into the way of predictability of the behavior of the sun. When you want to predict something, some activity, if it is periodic, it helps you. If it is not periodic, you have a problem. Okay. There are many predictable behavior of the sun that is there. You see the sunspot generally in solar maxima. It appears at the mid-latitude. It slowly drifts towards the equator, and you certain kind of polarity you expect, and then it comes to the equator, and that's how this butterfly kind of diagram exists, where the sunspots is coming from both northern and southern hemisphere. It comes to the equator in a cycle, but the preparation for the next cycle starts in this cycle itself. If you see, this is yellow, this is one kind of polarity of magnetic field. This is blue. Blue goes up to the polar region, and it comes down here during the next cycle. It is not random, it's predictable. That's how it happens, cycle after cycle. You see, now it comes yellow comes here. Okay, so that's how it is going. So that means there is a certain amount of order in the terms of the way the fields are getting produced inside the sun, which is to a great extent predictable, but to a great extent, under certain conditions, are not predictable as well. And that is where the challenge lies. Now, how do you observe, or how do you make sense out of it? You are sitting on a planet, you want to study the mood of a sun, you need to depend on, you can't land on the sun, first of all. You have to depend on something, okay? There are three factors, which is your weapon. One is magnetic field, 3 parameters. Another is radiation, and another is particles. These 3 parameters is actually, grossly speaking, if I summarize, synthesize, are our tools. The problem is that inside, from sun to earth, if you look at the plasma that is pervading the medium, there are almost like 13 orders of spatial and temporal scale. So the plasma which is here, vis-a-vis the plasma which is here and the plasma which is in the sun, they are very different in terms of their properties. Their scale sizes are entirely different on many occasions. So modeling this becomes difficult, because now you have to, at the interface of different medium, you have to make it consistent and then translate it to from the sun to the earth. That is a challenging thing. So predictability gets complex even when sun is behaving abnormally. The mood is violent, okay? When you have a solar flare, you have coronal mass ejection, you have co-rotating interaction region in the interplanetary medium, you have solar energetic particles. So these are the situations when sun is very active, okay? Even cosmic ray is controlled by how the sun behaves, which is coming from outside. So solar flare is this, it's an explosion on the sun. You generally measure it by the X-ray fluxes that is coming from the sun, that how explosive it is, the amount of intensity that you receive, X-ray intensity that you receive and you measure, that tells you that what kind of explosion, how strong the explosion is. Is all magnetic energy getting converted into other forms of energies? This is our measurement from XSM, from Chandrayaan-2. Some of you might have heard, and this is a This is a very sophisticated and very sensitive instrument. Like what I showed, this is GOES satellite, which is NOAA satellite, which measures X-class flares. Our instrument also, if you look at it, it is very sensitive. Here is a comparison of the GOES and X-class flares detected by XSM. And you can see the sensitivity because the lower class of flares, low intense flares, are also picked up by the XSM, which has been built in this very lab. Okay, so, and not only that, you get the spectrum here. So we have also made some progress, some significant progress in terms of, so keep this in mind. What I was telling is these three parameters are important for us in order to judge the or evaluate the mood of the sun. Radiation part, certain part we have addressed it, which is X-ray. The part which is not yet addressed is extreme ultraviolet. So that there are groups which are working on. Extreme ultraviolet is very important for the Earth's upper atmosphere, which is the space, for which the technology is being developed now. So that is one aspect you have to keep in mind. So when I say radiation, it's only X-ray I'm talking about. UV, ultraviolet, near ultraviolet was there in the Aditya L1 mission, but the extreme ultraviolet is something which we have not made so far. This is coronal mass ejection, and for reasons which we don't know under what conditions a CME will erupt from the sun, it does erupt. And if you look at the scale of the magnetic loop with plasma in it, is huge compared to the scale of the Earth. So this is coronal mass ejection, which can come. It's a magnetized plasma which comes towards the Earth's orbit. It disturbs the magnetic field, and you get a lot of disturbances in the near Earth space. This is something which is called stream interaction region. A fast wind coming and hitting, fast wind and slow wind, this is an outstanding problem in solar physics, solar wind physics is that what are the sources of fast wind? What are the sources of slow wind? Okay. It's not entirely clear to the community, and why those sources are producing fast wind and why those sources are producing particularly slow wind is an enigma. So this is the huge amount of hole-like structure, which are called coronal hole. Basically, it's a source of the plasma temperature is low here, so it looks dark compared to the background disk. It looks dark, but it's actually a source of fast solar wind. And when it comes and hits the slow wind, particularly during solar minima, when the entire medium between the sun and earth is pervaded by slow wind, this fast wind comes and hits it, and then it creates something called an interaction region. So it is called the that's why it's called a stream interaction region. It survives for a whole solar rotation, let us say 27-day rotation, then it's called a co-rotating interaction region because the entire thing co-rotates with the sun. Now, if Earth is trapped in this quagmire, then we have a problem of magnetic disturbances. So that's how it is important. Another thing is solar energetic particles. From CME, there is one kind of SEP, solar energetic particle come because the shock is there. CME is propagating with a speed which is more than the speed of the sound. And so it creates a shock in the medium. And then that shock, any shock that is there in the interplanetary medium, it acts as an accelerator. So it actually accelerates particles. And that becomes energetic. Particles become energetic, it becomes solar energetic particle. Why is this important? Because those particles, even if it falls on a circuit, it can damage it. So your space assets are vulnerable to the solar energetic particles that are coming towards you. And from solar flare also, the solar energetic particles can come. So this is another way sun can behave abnormally by sending solar energetic particle towards the interplanetary medium and towards the Earth. Yes, and as I was telling, it can damage you, the electronics there. The other thing is cosmic ray. Cosmic ray is an extra kind of galactic origin most of the time. It's a highest amount of energy that it contains. Its fluxes are less, but its energies are huge. And when it comes, they actually, it depends on the mood of the sun. If the sun is very active, there are lesser amount of cosmic ray particles that come to you. Because solar magnetic field is stronger, it will actually repel away those cosmic energy. It will not allow it to come to you. But if sun is dormant, then a lot of cosmic ray particles. That's why you see anti-correlation of cosmic ray in the initial slides that I was showing. this is an indicator proxy to identify what is happening when you are crossing the heliosphere. So Voyager actually saw cosmic ray radiation. It used this fluxus as a tool to understand that medium. Now, if you now summarize that the kind of particles that you receive at any point in the heliosphere, that can be broadly classified into three categories. One category is here, which the distribution looks like a Maxwell-Boltzmann distribution, where it is called solar wind. Then you see a long tail, but this long tail doesn't have a slope which is uniform. At up to certain point, you see one kind of slope and then another kind of slope. This is energy versus particles, fluxes or fluences. So these are the particles which are energetic particles. So its number density will go down, fluxes will go down, but its energy will go up. So the more the energy of the particle is, the fluxes of those particles will go down. That's how it works. Okay. But the interesting part is that these particles will give rise to this particle when it is accelerated by shock or any other process. These particles will give rise to this particle when it is further energized. So they are dependent on each other. And the reverse connection is also true. So when these particles get decelerated, they become this, and then they become this. So that's how the particle pool is working everywhere. So if you have to detect these particles, you can understand some of the way the medium is working. Then there are electrons, because we are talking about plasma is quasi-neutral, and electrons are also there. And electrons are coming through the magnetic field lines, and it carries the heat from the heat flux from the sun. So this is the heat flux which is taken away. And it's very important, if you can measure electrons, you can actually talk about the magnetic field topology in the medium itself. So electron measurements can be very useful. It's a little complex because electrons can come from other sources as well. If you have a satellite, even satellite can give rise to electrons. So it's not so easy to separate out electrons of medium origin or the origin from your instrument itself. That requires a lot of care to be taken. Now, there are exotic orbits that has been followed in the past. One such thing is called Ulysses mission of NASA. What it did is, it was launched, and you see it is 1998, and it came back. This is one orbit. It came back in 2004, 6 years, and 3 or 4 such orbits were taking place because of this mission. What it did is, it went out of the ecliptic. The sun and the planets are on a plane, which is called ecliptic plane. So the satellite was taken down and then went up so that it can collect particles which is coming from the sun, from the solar north pole and entire region. Okay, this is a very what I say, it is a very ambitious kind of a mission where it is going over the top of the sun, of the star itself, and coming down, seeing both the poles and detecting particles. It's not imaging, it's detecting particles. So it was not imaging, which was later on brought in by another mission, which is still on, which is solar orbit, I'll tell you. So what it saw is, in Ulysses measurement, it brought out that the solar wind during minima, this is the minima where activity is less in sunspot, it saw that equatorial region from the sun is actually giving rise a lot of particles. As you come to maxima, the particles are coming from all over the place. Okay, the velocities you can see, these are the velocity vectors. And if you can see, and then if you are in an intermediate region, you see it is intermediate to this picture and that picture. So that means sun is behaving differently in terms of particle when it is solar minima and solar maxima. Now, recent times, I think you might have heard about Parker Solar Probe, which went closest to the sun. It touched the sun. What do we mean by touching the sun? I'll come to that point. It didn't land on the sun. It touched the sun. That's the point. And it is actually went up to 6 million kilometers of the sun. Okay, so which is the closest of any man-made object that has gone towards the sun. And it has traveled at a speed of 430,000 million miles per hour, which is the fastest object humankind has made so far. Okay, and the distance, this speed is almost like 0.064% of the speed of light, and which it means that New York to Tokyo, it will take only 1 minute. And if you compare it with the Voyager speed, it's 38,000 miles per hour, and Apollo 10 is around 24,000 million per hour, miles per hour. Now, the point is, it's heat management, and that is where condensed matter physics is so important. Okay. If you want to go closer to the sun, your all instrument is going to melt if you don't take care. This instrument, Parker Solar Probe, functions. It functions to a great accuracy, even at that distance. And therefore, it uses a carbon composite heat shield. I'm not getting into the details of it, but that itself is a technological innovation in this field. Okay, 4.5-inch thick multi-layer carbon composites to stop the heat which is coming from the sun. In terms of solar orbiter, it doesn't go as close as Parker Solar Probe went, but solar orbiter goes out of ecliptic. It actually goes like the way Ulysses went out of ecliptic plane, but it is actually was able to image the solar poles. So what it does, Parker Solar Probe, what it did, if you go closer to the sun, this is the image that was taken by at the closest distance by Parker Solar Probe. What it did is, the solar wind, if you go towards the sun, if you keep on going at a certain distance, it's called, so you will find it's called subalvenic. When you say subalvenic solar wind, that means it's a slower wind, it's magnetically dominated. Okay. At a certain distance, it becomes superalvenic, the velocity goes up. And so solar wind starts accelerating from that point onwards. People were thinking so far, we didn't have any idea whatsoever that whether it's a surface which is not rough, what kind of surface we are talking about, which is called the alvin surface. Parker Solar Probe found that it's a patchy surface. It's not an uniform surface. And it went in and out of that alvin layer. And that distance is around 10 to 20 solar radii. Okay. Because it went into this medium, everybody called, because you are getting into the solar atmosphere. That's why people said that it touched the sun. Okay. And solar orbiter, what it did is it actually tilted the orbit and it went down and looked at the pole of the south pole of the sun. And it saw something which has not been photographed before. And they saw the magnetic polarity of the source region. And they saw an indication that the flipping of the magnetic polarity has already started there. So the thing that I was talking about through a butterfly diagram is an imaging proof of what is happening there. These are exceptional measurement in terms of the way it is approached. It's not easy to make such kind of measurements. Another important thing that Parker Solar Probe saw, which is called magnetic switchbacks. So as it was approaching the sun, it actually observed a S kind of structure in the magnetic field. As it went closer to the sun, it saw those kind of structure and it started increasing in frequency. So it was like this. So Parker Solar Probe went like this and it saw that kind of switchback structure. You see this structure in hilly railway tracks. Okay, so instead of ascending the railway line, if you see in many places, earlier it used to be there, if you can Google it, the switchback is they go like this and then they go like this, railway track, then they go like this. So instead of going this way, which is not possible, it is called switchback. So they change the switch. So the train goes like this, then switch is changed, it goes like this, then again switch is changed, it goes like this. And that is how the ascending takes place. It's called technically switchbacks. So these are named as magnetic switchbacks. The importance of this, that how solar wind gets accelerated, that is something which is an outstanding question. So magnetic switchbacks, people found that this can get connected with the nearby field line and then they get dislodged. And then when they get dislodged, they can take solar wind particles along with it and it can cause great acceleration there. It's like a whip cracking effect. If you see in circus, the tiger, the master actually take a whip and there is a peculiar sound that comes. And it's a kind of structure which is that. So it actually cracks it at some point, this sound comes. So it comes with a folding and eventually breaking it with a high speed. So that's kind of structure that is come, which is switchback, is very important because it appears that it's not yet a settled issue. It appears that this granular structure, which are top projection of the convection cells that is going on, those structures, from there, these switchbacks are coming. So as you come closer to the solar surface, you are seeing more and more switchbacks, and eventually you come to the solar interplanetary medium, and then eventually everything gets diluted. You hardly see, it's very difficult to detect it from, let us say, L1 point. Okay. Now, this solves a particular, this solves a question and poses further questions. Like in every challenging branch of science, this solves a question that how solar wind is accelerated, maybe switchback has a role, but how switchbacks are getting created, there are multiple theories people proposed. And one of the theories only I just told here. Another mission is stereo A and B. So when you are sitting at a point and looking at a sun, a CME getting erupted, it is actually a projection on the sky. It's a 2D projection, two-dimensional projection. You don't have any idea about the three-dimensional structure of that CME, which is important because if you want to evaluate its impact on you, you need to know that how three-dimensionally it looks like. Because on 2 dimensions, so for example, if you have a screen and if you have a shadow of you and your friend's shadow on the screen, you may not be able to distinguish that how and what kind of three-dimensional structure you are or your friend is. Okay. Although, because you are projecting it onto the two-dimensional surface. So exactly that's what happens if you are not a 3D projection measurement you are doing. So stereo, what it did is, one of the stereo satellite is sat here, another sat here, and both of them kind of co-rotated, rotated around the sun. One is called ahead, that's why stereo A, ahead of Earth. Another is B, which is behind the Earth. It's almost like Earth's orbit, slightly less and slightly more. That's how it was planned. And then it actually gave some unprecedented structures of the CME in 3 dimensions, which is important because to assess that how the CME that is coming towards you, how accurately you are making the measurement. Then there is Solar Dynamics Observatory. I'm telling this just to tell that what kind of progress has been made. Okay, and what kind of questions that has come because of that progress itself. And Solar Dynamics Observatory, it actually had 10 different wavelengths. So these wavelengths are, it is the wavelengths which are coming, these emissions are coming from different layers of the sun, some photosphere, chromosphere, transition region, different layers. Okay. And so if you look at these wavelengths, certain features are here, it is not here. Okay, so that means this is happening at a certain altitude, which you are capturing. So if you now make a composite of these images, you know that how that particular process is taking place in terms of altitude of the solar atmosphere. This is kind of a very, very novel way to look at and some of these approaches is there in our Aditya L1 mission also. I'll come to that. Okay, so this is important because it can, particularly for solar flare, this is important because how those explosions are taking place from a lower height and is going at an upper height. For that, you need to measure it at multiple wavelengths which are coming from multiple altitudes, height of the sun, solar atmosphere. Another mission was Helios. Helios, it took a different approach. It took a heliocentric approach. It went up to 0.3 solar AU, came back at 0.8 or 9 AU and tried to measure. Now, it started a different field altogether because before that mission, nobody knew that how solar wind properties will change as you come from the sun to the earth. What Helios saw that solar wind, when it is coming, you expect that the temperature of the plasma that is coming, because it is expanding, solar wind is expanding in the interplanetary medium, it's an adiabatic expansion, the temperature should drop. Ideally, it should, okay? But closer to 1 AU, if you see electron temperature and other temperature, if you model it, it doesn't follow this. It actually changes, it heats up. for reasons which have been addressed later. Some of these aspects are understood, some of these aspects are not understood. So what it means is that it doesn't follow exactly the adiabatic expansion that is initially predicted, that solar wind will expand and it will cool down the plasma, and you will eventually see, you will be able to model it from when it is coming from the earth to the sun, sun to the earth. So now these are some of the missions that has taken place. Having said that, our interest eventually is not only to understand the sun, but how it's going to impact us. Okay. And that is affected by, that is known by space weather. Space starts from 100 kilometers, the so-called Kármán line, where the aerodynamic control goes away, the other controls come in. And so from there to sun, everything, or in the heliosphere, everything is space. Medium properties are different, but it's space. So space weather is actually different plasma domains. Here the plasma properties, here the plasma properties, and here are very different. So that's why space weather prediction, which is very important for very technological applications, is very difficult, because you are talking about different plasma domains and how they are actually coupling with each other. So the primary questions are this: the way the space weather predictions will work. We need to understand the physics of it very clearly so that we can couple 13, as I said earlier, the 13 scales we are coupling from sun to earth. Okay, 13 spatial scale, right from gyroradius is a scale, or mean free path is a scale. Okay, so solar wind mean free path from sun to is actually almost like 1 astronomical unit. Or gyroradius, if you take maybe few hundreds of meters. So you see the difference in the scale sizes, and you have to combine them. Okay. Why it is important? Some of the example is, you have International Space Station, and India is going to have one in 2035. The space station maintenance, it is at a height of 400, 450 kilometer. And whenever there is a solar disturbance, the atmospheric drag changes. And the space station, there is a drag effect. The space station comes down in altitude. And there is an operation which you have to take it up. And this goes on. This cat and mouse game goes on continuously. So you see, it comes down, and then there is a booster fire, and it goes up. Comes down, goes up. So that's how the maintenance is taking place. This is an event which happened because of a solar disturbance that was not so modeled isn't correctly. And the consequence of it, the Elon Musk company, SpaceX, they actually gave. What happened is they lost almost like 38 satellites because they actually put the satellites at a parking altitude, because to reduce the launch cost at around 220 kilometer height. And whenever there is a need, they will replace the satellite at 350, 400 kilometers. They will take it up and then place it there. But before that, they will put at a configuration where the drag is minimum at 220 kilometer height, that they call it parking. Now, what has happened is the solar disturbances that this satellite encountered, this is not so great. So the model prediction, empirical model kind of prediction, couldn't predict it. And their assessment was wrong. So the drag, they couldn't control it, the satellite came down. Okay, so that's how it can affect you. It can affect radio communication because ionosphere is coming in between. Ionosphere becomes turbulent during quiet time, and when sun is disturbed, that is the time also. So any satellite to space communication, you have a problem. Okay. So again, I'm bringing you back to start with. I was talking about radiation, magnetic field, and particles. So I talked about the radiation. Let us talk about the magnetic field. The solar wind has a magnetic field embedded in it. That magnetic field is this. If its polarity is opposite to the Earth's magnetic field, it actually connects with the Earth's magnetic field. And because solar wind is flowing this way, it carries that magnetic field on the night side. Eventually, it gets reconnected here, and it actually stretching a string and releasing it from there. It comes back with very high speed towards the Earth. That's what is happening and eventually what happens is the entire magnetosphere is turbulent. Okay. So that happens, the preliminary condition that started is the IMA-BZ, means the Z component, which is the north-south component of the magnetic field of the solar wind, which is just opposite. And it so happened at a distance of the Earth's orbit The Earth's magnetic field is almost equal to the solar wind magnetic field. So if you change the polarity, it's just an ideal condition for reconnection. And then the associated configuration changes in the magnetosphere. So these are some of, and so this movement which is coming here, this is affecting, coming to your geostationary satellite. So it can affect your systems. Another thing which can affect your system is something called substorm. Magnetosphere itself stores energy because you are stretching it. You're like a rubber string. You are stretching it. Now, if there is some trigger from solar wind, suppose magnetic polarity of the solar wind changes or pressure changes, or if nothing changes in the magnetosphere, there are plasma instabilities that is releasing some energy, okay, that also can change the magnetic configuration suddenly. Something like this will be happening here. And that will cause something called substorm that can happen. Okay, you look at this, it will create a magnetic field which is opposite, and it will connect with the Earth's magnetic field, and it will drag it downside. And then somewhere here, normally reconnection takes place at a far longer distance, but it will happen here, and then particles will rush through and get deposited in the polar region. This is why on the night side you see aurora. Night side, you don't see aurora for storm. What you see aurora is because of substorm, and this is the process that goes on. Okay. Now, when you want to study this, you need vantage points where that can help you to study this. What kind of vantage point that you can use? In a three-body system, there are 5 vantage points which are called Lagrange points, which you can use and where you can park a satellite. Now, this parking is very different from parking around a gravitational body because there is nothing there. Okay, so you need to keep that satellite, you have to maintain it in that orbit. Okay, so these are 5 Lagrange points. Analytically, if you want to solve it, it's a 3-body problem, you cannot solve it exactly. Okay, so Lagrange actually makes some approximation and solved it, and these 5 points actually was the solution of that problem. And so, in these 5 points, Lagrange, the first Lagrange point is here. Lagrange point 2 is here, where James Webb Space Telescope is there, which is used for astronomical observation. They want to look at the deep space. They don't look at the sun. They want to look at the deep space, so it is at L2. So it is pointed in deep space direction, James Webb. Aditya L1 is here. Not only Aditya L1, the other NASA satellites are also there. And you can't park a satellite at a point. You have to move around it and continuously look at the sun. That orbit is called halo orbit. There are different kinds of orbit that is possible. One is Lysage's orbit, which is not exactly halo orbit. This is halo orbit, but Lysage's orbit is slightly different, which is kind of a periodic thing. This is periodic. Okay, and it is not in one plane, but in both the planes. Okay, so it is this plane as well as this plane. Now, what has happened is that Aditya L1 satellite, so India has launched Aditya L1 to study the sun. Now, where exactly India has put the satellite is at L1 point, and then there is no eclipse. You can look at the sun continuously. The advantages of these points, L1 point, is threefold. One is it can look at the sun 24/7. Second is it is out of magnetosphere, so it is pure solar wind is measuring. And the third is that at L1 point, the solar wind velocity, if it is maintaining, with that velocity, you have 45 minutes to 1 hour of lead time you are getting. So you have some advantage. So if you want to use that point, that measurement as a forecasting facility, you can actually do that. Although it's a science mission, these are possibilities. In future, there can be effort from India also, where this kind of mission can be used for, particularly for forecasting purposes. NOAA in US does that through different satellite missions like Discover and other missions. And recently, SWIFO L1 mission. So this is the satellite I'm talking about. This is our mission. And where you can see these are the instruments that are placing there, and our instrument is somewhere here and somewhere here. So it's all over the spacecraft. One for low energy solar wind measurement and another for high energy solar wind measurement. Okay. So there are certain instruments which is there to look at the sun remotely, like what kind of coronal mass ejections are coming out, what kind of flares are happening. So those are remote sensing instruments. So those remote sensing instruments are 4, and there are in situ measurement, which is measuring solar wind sitting at that position. Those are called in situ measurement, and our instrument is one of the in situ measurement. Although we are giving the name of one instrument, is actually consists of 2, because we have a 2 different system clubbed into one for low energy spectrometer, low energy measurement, and high energy measurement. Aditya L1 primarily was conceived because to accommodate a coronagraph, which will block the sun and look at the outer layer of the atmosphere of the sun, which is called corona. It is difficult to measure corona if you don't block the sun, because the solar disk is very, very bright. It won't allow you to measure anything in the solar atmosphere. You have to block it so that you can look at the corona. VLC has an advantage that it has a coronagraph which SOHO at present doesn't have. Okay, means it can look very close to the solar surface, which SOHO doesn't have. SOHO actually launched 3 coronagraphs earlier, but the coronagraph which is supposed to look closer to the solar surface or photosphere, that got damaged. So VLC is now measuring in that region, so making some very important observation in that area. The advantage is that you are right at the inception of launching of those disturbances like CME, coronal mass ejection. You are looking at the region where it is getting formed and getting launched. So you can actually study it from the inception. Yeah. Then SOOT is a solar ultraviolet imaging telescope, which is looking at the sun in 11 different wavelengths. And why these 11 different wavelengths are because of photospheric and chromospheric and transition region lines, but in the near ultraviolet, 200 to 400 nanometer line. And these are some of the lines which have not been attempted earlier at all. So these are very unique observation in some sense. Okay, so this will help us to understand when a flare is erupting. So that will be able to capture in multiple wavelengths. Then there are X-ray instruments like XSM. There are Solex and Helios for low energy and high energy measurements, Solex and Helios. That is because X-ray is an indicator of is a solar flux which is coming at high energy during flares. And so that can be, that is there. So this is also one of the remote sensing instrument. This is observing sun as a star. It's not discriminating. It's not able to, it will not be able to identify the location. But if there is a flare and if there is a solar X-ray flux which is increasing, it will be able to tell you that there is a flare that has happened. And there is a magnetometer which is measuring the magnetic field which is coming with the sun, which is important because I told you that that magnetic field will generally offset the Earth's magnetic field, giving rise to the effect that you are getting, space weather effects that you are getting. So as you can see, there are 3 things we talked about. One is magnetic field, another is particle, another is radiation. So magnetic field is measured by the magnetometer which is on board. It's a flux gate magnetometer. There are 2 of them, and then differentially it measures. So these are some of the comparison which shows that it's working well, and these are our instrument aspects, which consist of 2 spectrometer, as I said. So these are the flight models of aspects, and as you can see, there are one is looking at a plane, another is looking in perpendicular plane, and this is the lowest energy spectrometers, and these are the high energy spectrometers. And interestingly, we focused on the science part of directionality. And we thought that directionality and alpha proton separated measurements, which is the major constituents in solar wind, will give us a lot of unique information. So as I said, that our instrument is actually spread all over the spacecraft, which is here, here, and on the back side of the spacecraft as well. Here also it is there, is the high energy spectrometer. I have come to the last part of my talk, last 2-3 slides, where I want to show you that some of the recent results, a couple of recent results that we have got from aspects, which is fundamentally very new in the sense that through the steps measurement of energetic particles, we have shown that Parker transport equation is very well known in terms of energetic particle generation in the heliosphere. That was developed, theoretical formulation of it has been done long back, decades back, I mean, few decades back. Okay. That primarily, it explains the energization of particle, but with the assumption that to start with, you take some kind of seed population, which is also energetic, but then you accelerate them to make the energetic particle. When you take the seed population, you make an assumption that they are directionally isotropic, okay, in the medium. Now, if it is not directionally isotropic, it will eventually the kind of particle you will produce through theory is not the same thing as you will get into through measurements. Okay, so verification of that particular foundational assumption is very important. Okay, so because we have directional measurement available, we thought that this will take it up and to verify this under what conditions this kind of foundational assumption is valid. So this theory was proposed in 67, 65 or 68 or some, I forgot the year, but there is no experimental verification available. So people were using this, but there was no verification for that. So we showed that if you take the time duration shorter as a few days, this particular assumption is actually experimentally correct. We actually proved that this assumption is correct, and if you take the period for a few days, but if you increase the period and observe particles, what happens then? The external influences come in picture, and then this assumption you will not be able to, will not be valid. And this is another result which has come from low energy spectrometer, where you can see this is a famous May storm, solar storm, where almost like 7 to 8 CMEs came and they interacted into the interplanetary medium. The problem with CME is that if multiple CMEs come, your problems of prediction becomes even more complex, because with one CME, you can make some prediction by modeling it. If there are multiple CMEs coming, the way they will be interacting, they will change what we call as geo-effectiveness. The geo-effectiveness is going to change because it will alter the magnetic field and the entire structure of the CME, because they will be interacting with each other. Okay, because these are plasma and magnetic fields. So what we saw is in two planes we measured, because our instrument can measure 360 degree in one plane and 360 degree in the perpendicular plane. We saw structures which has not been seen earlier. Okay, particularly this structure, where this is a site of energization of particle because of the shock that has happened at this place of time. And this sustained for 13 hours. The shock generated energetic particle for almost 13 hours. So this has not been reported earlier, and we actually showed that this is happening. And 13 hours, it's almost preserved when the CME-CME interaction, 8 CMEs, they were interacting with each other. It actually got preserved and propagated like this. So with this, I have come to an end of this. What I'm trying to say that we are at a very exciting phase of solar science or solar wind science or space weather science. And we have started understanding the physics of the sun in a much detailed way. But as we are understanding, more and more intricate questions are also coming into picture, new questions. And so we need a continuity of these missions to understand it with better instrument and modeling efforts to understand it. Aditya L1 is the first step towards this particular goal. We also want to have a mission which is called Disha, which is a dual satellite aeronomy mission, which is on the Aditya mission is giving us the driver information. Disha will give us the impact information. At a 450-kilometer height, this is a dual satellite mission. We want to have an overlapping observation between Aditya L1 and Disha, so that we know that this is the driver and this is the impact. That will help us to have a global model so that we can predict the impact in a much better way, maybe 10 years down the line. And this is from an application point of view. This is the science point of view I was talking, but from an application point of view, because we are a spacefaring nation, we have increasing space assets and footprints in space. And we also would have the Bharti Antarik Station in 2035 and an Indian astronaut on Moon in 2040, and maybe a lunar colony there. So it's important that the the space weather aspects are actually gaining a lot of importance because you are putting not only space assets into space more and more, but also Indians in space. Okay, so there is a need for a Indian Space Weather Prediction Center, for which the initiative has already been taken by ISRO, and we have started working on this. So with this, I conclude here, and thank you very much for your attention.
Session. We thank on behalf of IAPT. And the floor is open for a question and answer some of the questions, please.
Yeah, thank you, Deepu. Very wonderful talk. So my question is, you mentioned that there is this adiabatic expansion. One cannot account this cooling of the solar wind by considering the adiabatic expansion. So the question is whether it is the lack of the quasi-static, the adiabatic expansion is not that fast that the heat is getting into, it's like becoming partly isothermal, or is it basically adiabatic, the quasi-static condition is not met, but there is a preheating, because there is this wind coming from the sun side and is heating the mass. So that is why the adiabatic condition is being violated. So what are your...
Yeah, the reason
Yeah.
is,
Thank you.
as per today's understanding, is the kinetic processes are coming into picture. And if you look at the temperature of solar wind, at this, as you come closer to 1 astronomical unit, means closer to Earth, the perpendicular temperature and parallel temperature, they start differing. They are not the same. So that means there is a isotropy is now not maintained. So if the medium is becoming more and more anisotropic, what it essentially means is it has a lot of free energy, and then it's a site for instability generation. It basically happens because kinetic processes are set in there. So it is no longer adiabatic because there are wave particle interaction and other processes are also coming into picture, gaining energy in certain directions and losing in certain other directions. So it is in adiabatic expansion. So within this system, the energy is actually getting partitioned in a very different way. So that's the reason that is happening. Yeah.
Any other question from students? Yes, please.
Yeah.
Yeah. Yeah. Yeah, my mic is coming.
So first of all, thank you for this wonderful talk. So I am basically from experimental optics. So my question is that how you are blocking the sun for the coronography. So can you just explain how it is?
Okay.
Yeah.
So it's called an occulter. So what it does is that in front of the optics, you put an obstruction in such a way that the angular dimension of the object you want to occult in an artificial manner. Okay, so you make the design in such a way, it exactly blocks the solar disk in such a way that when the optics is seeing that, it's actually it's excluding that area. You're scooping it out of your field of view and then looking at the peripherals. So that's how it's a mechanical occulter which is put at a certain distance in a certain size you decide, and then you put it that way so that the main disk is blocked. So you are creating an artificial solar eclipse in this manner through your design.
So is it, I mean, can it be offered for a expandable field of view, or, I mean, if you talk about the field of view?
It can. So to give you it's a good question, because in Soho, the field of view, there were 3 occulters. Okay, C1, C2, C3. C1 didn't work, and that place is being taken by VLC from our mission. C2, C3, now in Soho, C1, C2, C3 are seeing you are going more and more out of the solar atmosphere. So they were using this, the FOV they have varied. So they have increasing FOV to look at the outer portion of the atmosphere. So you can actually change the FOV accordingly and look at the radially outward portion of the solar atmosphere. Yeah.
Okay, thank you.
Thank you.
Thank you, sir, for the wonderful talk. I really enjoyed it. By the way, I don't have any question, but I want to give one comment on the correlation between condensed matter physics and space science. Like the formation of vortices in position space in galaxies and these Milky Ways has long been observed in space science. And quite recently, it's been observed in topological materials, even at the quantum scale. So that's why I was really thinking like it's so important to listen to such kind of talks, that they're kind of smooth transition from macroscopic scale to the microscopic scale. Thank you very much for the wonderful.
Thank you. Thank you for bringing this up.
There was one question out there.
Yeah.
Yeah.
Please tell your
Yeah.
name and from where you are if you are a student. So
First of all, sir, thank you for the wonderful talk. I'm Nishit Karodra from Gujarat University.
Yeah.
Sir, I have a question on graph. You mentioned that the graph was on energy versus flux of particles, Maxwell boson. So I had a question that you mentioned that there was a particle gives rise to another particle.
Yes.
So there was a conversion, or what I want to.
Okay. If you look at that curve, maybe I'll put it if it is there available. Yeah. Yeah. This is the one you are referring to. So if you look at that curve, now this is low energy, because now you see generally in particle measurements, you measure something which is called as directional differential flux. Okay, so you make energy beams and then in a certain direction. So you normalize with respect to steradian, with respect to area, with respect to energy, with respect to nucleon. But this is called fluence. Fluence means you are not doing with respect to time. So because this flux, as you go to higher energies, this is integrated over a large period of time. You can see it is for 3 years. Okay. So if you directional differential flux, if you integrate it over a large period of time, is called fluence. So it's a fluence spectra. Okay. Now, why it is done? Because as you increase your energy, the flux that you gave is very, very small. A galactic cosmic ray, the flux of it is very less compared to the solar wave. So if you have to plot the entire spectra on a single curve, it is a problem unless you integrate over a large period of time. So that is why it is called in 3 years. Now to answer your question, that these particles, when you accelerate it,
Yes.
So when you accelerate a particle, you require a slightly lower energy. For any particle acceleration, there is some energy which is called injection energy is required. In the shock, suppose if shock is accelerating, it has to cross the barrier of the shock. So it requires certain injection energy. Without that energy, without that initial energy, it will not be able to, or it will not be eligible for acceleration. Let me put it this way. Okay. So if it has certain energy, it is crossing the shock repeatedly, it will get accelerated and eventually goes out with a higher energy. At every crossing, it will gain some energy of the shock front. So this energy is as a injection energy for this energy, which is getting a little higher energy. And this will give rise to this energy. So that is how it is. One energy is giving rise to another energy. So yes, that's perfectly all right. So at any given point of time, every one of them is present. But interconversion is going on. It's a loop that is going on from higher energy to lower energy, as well as from lower energy to higher energy. It's always going on.
Thank you, sir. Thank you.
Thank you.
Okay. Someone from backside?
Yeah.
Anyone? Actually, sir, I just was thinking, as you mentioned that on all these Lagrangian points, they're not stable.
Yeah.
So obviously we need to maintain our satellites and other things. So will they also be like adversely or favorably affected by the solar activities and all that?
Solar activity will affect
Will be there.
any asset, space asset, which is there in space.
Right.
Okay, they may affect. Sometimes a single event upset can also happen, where a single particle with very high energy falls on a circuit and destroys it. Okay, so that, but then with sufficient precautions are taken to make it radiation hardened, all the components that are using.
Right.
So you actually decrease the probability of that kind of events
effect.
happening to you. But this, even among the Lagrange points, some of the points are more stable than others, like L4 and L5, which are more stable than L1 and L2 and L3.
Okay.
Okay. Although we have put it in L1, L4 and L5 are more stable because of the depth of the potential, the gravitational potential that you have. So particle which is going there is having a larger gravitational well to settle down.
Okay.
Okay, compared to L1 and L2. In L1 and L2, you give a certain energy, which is, if there is a mismatch, it will go in one direction. So you have to bring it back. So some orbit maintenance is required for that. Okay, so but L4 and L5, little maneuvering, it is still needed at L4 and L5, but it will be relatively more stable. But there is a disadvantage of L4 and L5 is because it is more stable, any space objects will also go there and Trojan sources will also get accumulated there.
As in
like asteroids, small stone pieces. Okay. So they will also be trapped at those places as well because it is relatively stable.
Right.
So these are all the plus and minuses of this.
So I mean, is there any specific reason why we chose L1 or?
Yes, because it was a sun mission. It's a dedicated solar mission. So we wanted to look at the sun 24/7.
Right.
And so that's why we chose L1 point. In future, who knows, we will have satellite at L4 and L5 as well.
Do other countries have L4, L5?
L4, there is a plan by European Space Agency. That mission is called Vigil. Vigil, their timeline is 2031. Initially, when Professor D.R. Rao was our ATCOS member, he was actually talking about L5 mission as well. But then that we somehow, the focus went into L1 and then that didn't materialize at that point of time. And so European Space Agency has come up with L4 mission at 2031, which is called Vigil. The advantage is some of the space weather disturbances are easier to track much in advance from L5 point, because you are looking at a particular side of the sun, which is rotating and coming to Earth directed. So it is looking at much earlier, compared to when it is rotating. And
you get some maneuver time.
Some maneuver time, and you can transmit that information, so that you get lead time there. So that's the advantage of from a space weather forecasting point of view. Yeah.
Good, very nice. So is there any other question from students? Okay, YouTube. Can you spell it out?
Hey, there is a hand raised.
Yeah. Please give the mic over there. Yeah. Perfect.
Hello.
Yeah.
Nice talk. And I'm Aishanu Patel, and I'm from Aizer, Kolkata.
Slight louder, please.
Okay. I'm Aishanu Patel, and I am from Aizer, Kolkata.
Okay.
And my question is that, like, you said that the mean free path for the solar winds is like close to 1 astronomical unit, right?
Yes.
So what will be the significance of that, like, given that like it is like close to the orbit of Earth, right?
It is an now I'll actually phrase a question based on that, which will help you to understand. If mean free path is 1 AU, now if you look at this curve, this is Maxwell-Boltzmann kind of Maxwellian curve, right? And you derive solar wind temperature from this. Now, if mean free path is 1 AU, that means there is hardly any collision between when the solar wind is coming from the sun to the earth. If there is no collision, ideal gas laws will not be valid. If ideal gas laws are not valid, then how do you derive temperature from a gas? Plasma is a gas, let us assume. But you are deriving, and it looks like reasonably Maxwellian. So the question is that what happens that even if mean free path is 1 AU, you still have a Maxwellian distribution. Something is taking the place of collision, which is kind of you have a Coulomb interaction between the solar wind particles or maybe wave particle interaction. They are actually taking long range forces, even if they are sufficiently apart. It is acting as an influence on the other particle. Otherwise, this is counterintuitive because if it is mean free path is 1 AU, you are not supposed to get a Maxwellian. Right. So, and many occasions when we actually invert the data to produce space weather parameter like solar wind density, velocity, many times you see that there are drastic departure from this. So on that occasion, there are other processes that are working on that. If you assume that your instrument is measuring correctly, which you can verify, then also there are occasions when it is not Maxwellian. So that means there are other processes which is actually making it deviate from the Maxwellian term. So the implication of its mean free path is 1 AU, but which is a fact. So it hardly it's a collisionless plasma, but still you are treating it as a Maxwellian fluid. That's a very interesting aspect. Initially, when I started with this field, this actually bugged me for quite some time. I still do not understand fully the 100% of it, how it works, but this is a fact that we get Maxwellian, but sometimes it's not. Most of the time you get the whole prediction or whole space with solar wind science is based on that you get solar wind parameters from this. Although mean free path is 1 AU.
Okay.
Yeah.
Okay.
Yeah.
Thank you.
Yeah.
Yes. Yes.
Yeah.
Yeah. So we readily observe the amalgamation of maybe optics and condensed matter
Yes,
and
yes.
the fundamentals of physics and all that.
Yeah.
So meanwhile, we'll take a question from YouTube. Will you please? Will you? Yeah, we can please spell it out.
Yeah, there is some question or comments and some question. So I will just pick one.
Yeah.
So the question is, can external perturbation affect the heliosphere of sun, and what would we observe, and what would be the result? So an external perturbation effect on the heliosphere of sun.
External perturbation in the sense, if I take cosmic ray as an external perturbation, it doesn't perturb the heliosphere, but its distribution within the heliosphere can change significantly depending on how sun's activity is. But the Milky Way, so external perturbation, when I say any perturbation in the local interstellar medium, which is at a smaller time scale, is nearly not much of perturbation is imposed on the heliosphere. But at a larger time scale, because the entire galaxy is rotating in a million-year time scale, and so on a larger time scale, there can be. But at a smaller time scale, we don't see any conceivable or detectable signature of perturbation which the external factors are sort of exerting on the heliosphere.
Yeah. Okay.
Except the cosmic rays.
Okay. Thank you.
So, any other question? Anyone student inspired? Sir.
Yeah.
Sir,
Please.
yeah. Sir, please take the mic.
Please
take.
How do we understand actually from the magnetic field distribution carried by the flux, solar flux, by the reversal of the Earth's magnetic field, time scale involved, or how you can predict actual reversal? And is there any comment on that?
There are two things here. It's a very interesting question. That if you take as a shorter time scale, okay, the solar wind comes with the embedded magnetic field, as a topology of that is an undulating surface. So if Earth's orbit is within that, you take it as a bed sheet, let us say. And if the Earth's orbit is within that, inside, you get one kind of polarity of magnetic field, which is solar magnetic field. So it's north-south direction because it's three-dimensional undulation. It's polarity in this direction may change if Earth is on the top or Earth is on the bottom. So depending on that, you can have different kind of interaction with the Earth's magnetic field. Provided Earth's magnetic, now this is for shorter time scale. Okay, so if it happens to be the case that the Earth is at a point where the Z component of the magnetic field is just opposite, then that interaction is favored. So it will destroy or it will affect the Earth's magnetic field because Earth's magnetic field is northward, and if that magnetic field is southward, solar magnetic field, they will actually is a favorable condition for reconnection. And so it will disturb the Earth's magnetic field. But on a longer time scale, it is even more, so various paleomagnetic people, they do that. Earth's magnetic field is not steady. Like the way Sun's magnetic field is reversing, Earth's magnetic field is also reversing in a geological time scale. That's the question. That's why first shorter time scale I wanted to address. And that is in the last 77 million years, I think that has happened 25 times. If you look at the recent, in 2016 or 2017, there are two Nature papers which came, which showed that in the northern hemisphere, the North Pole, it went from Siberia to Canada. Southern hemisphere, not much of change was there. In the northern hemisphere there, if you look at India, the equatorial region is actually sometimes over Trivandrum, sometimes over Sri Lanka in the last 100 years. Okay, so there's something which is going on. Whether this is a precursor of is an imminent magnetic field reversal or not, that's a question nobody knows at present. But it's a fact from paleoclimatic history or the other stressors that people have studied that it did reverse. And when it reversed, and the simulation, there are a lot of simulation work there. And so when it reversed, it takes almost like few hundreds of years to get back to the again dipolar configuration. In between, it's all multipolar configuration of the Earth that the simulation tells. Well, this will severely, it will go out of the window. I mean, if we happen to be in that stage, life on Earth will be problematic. Earlier also it has happened. Right, right. So yeah, it's a large time scale, million years time scale. So that's another thing which is a different field altogether. People do a lot of simulation in that regard. So there's a multipolar world literally at that point of time.
All right. So if there is no more questions, then thank you, Professor.
Thank you. Thank you.
We now move to the felicitation of our distinguished speaker. May I invite Professor K. Joshipura and Professor P.C. Vinod Kumarji to kindly felicitate Professor Dibyendu. Thank you.
Thank you so much. As a token of our appreciation and love, we are very happy to present first a gift and then a memento. This is our annual magazine, Pragami Tarang, which means progressive wave. And this is our annual activity, and we would request you to write an article in this magazine. It will be in English. This is partly in English and mainly in Gujarati. So our pleasure. Thank you. Very nice of you. Very nice. Oh.
I see.
Oh. You agree that to gauge and judge the mood of a star we have to first set and update our own group. Therefore, a shortly mark would be very helpful.
Thank you. Thank you. Thank you.
As we approach the conclusion of this evening's program, I invite Professor Videsh Thakkar, IAPT RC07, to propose the vote of thanks.
It gives me immense pleasure to extend the vote of thanks on behalf of IAPT RC7 on the occasion of this 8th PRL IAPT Dr. Vikram Sarabhai Lecture 2026. First of all, I would like to thank the Director PRL, Dr. Anil Bardwaji, for his continued support and felicitating this lecture today in this beautiful K.R. Ramanathan Auditorium of PRL. Next, I extend our gratitude towards the speaker of today's event, Professor Dibyendu Chakrabarty, Head Space and Atmospheric Sciences Division PRL, Ahmedabad, for sparing his valuable time from his busy schedule and delivering such an insightful talk on the mood of a star and space weather. In this presentation, he actually talked about the activities of our star, the sun, and its effect on the earth. He also wonderfully responded to the queries of the audience as well as from the YouTube. So thank you, sir. I also thank Dr. Bhushit Vaishnav, the academic head of PRL, for making all the necessary arrangement for today's event here. I would also thank the National President IAPT, Professor P.K. Ahluwalia, for allowing us to organize and continue with this lecture series. I also extend my warm wishes to all the office bearers of IAPT RC7 to make this event successful. And of course, how can I forget the wonderful audience here who have come from different corners of the state of Gujarat and maybe from our country. So thank you for coming and attending this wonderful lecture and this event. Finally, I thank all those who have directly or indirectly contributed for the successful execution of this program. Thank you all.